We've spent 14 episodes deep inside neural networks. Now we step back to the classics, the algorithms that came first and, on most real world tabular data, still quietly win. We start with the two you should always try first, linear regression and its sibling for classification, logistic regression. Here's the truth the hype skips. For images and language, deep learning rules. But for the spreadsheets that run the actual world, prices, risks, churn, demand, simpler models often beat giant networks. They're faster, they're interpretable, and they need far less data. This block is those workhorses, starting with the most fundamental of all. Linear regression does one thing: it draws the best straight line through your data. Give it a feature, say house size, and it predicts a number, the price, by following that line. More features just means a flat plane in higher dimensions instead of a line. It's the simplest possible way to turn inputs into a prediction. And look closely at the formula. The prediction is each feature times a weight plus a bias, a weighted sum. That's exactly the neuron from episode 1, minus the activation bend. Linear regression is a single neuron with no nonlinearity. Every deep network is, in a sense, thousands of these stacked and bent. We're back at the atom. How do we find the best line? The same idea was our loss episode. For each point, measure the vertical gap to the line, the error. Square those errors, add them up, and find the line that makes that total as small as possible. It's called least squares, and for linear regression, there's even a clean formula that solves it in one shot. No gradient descent required. Here's a superpower neural networks lose. You can read a linear model. Each weight tells you exactly how much its feature pushes the prediction and in which direction. Size has a big positive weight, age a negative one. That transparency is gold in medicine, finance, and law, places where why matters as much as what. The model isn't a black box, it's a sentence. Linear regression predicts numbers, but often we want a category. Will this email bounce? Is this tumor malignant? Yes or no? If you force a straight line onto a 0 or 1 label, it misbehaves, shooting above 1 and below 0, predicting impossible probabilities. We need to bend the output into the range of a probability. And we already met the tool, the sigmoid. Take the linear model's raw output, any number, and pass it through the S-curve that squashes everything into 0 to 1. Now the output reads as a probability. Big positive input, close to 1. Big negative, close to 0. Right in the middle, 50-50. Put those together and you get logistic regression, a linear model wrapped in a sigmoid. It takes the weighted sum of the features and returns the probability that the answer is yes. Despite the name, it's a classifier, one of the most widely used in the world, and it's just a single neuron with a sigmoid activation. The neuron again. Geometrically, logistic regression draws a line, or a plane, that separates the two classes. On one side, it predicts yes, on the other, no, and right on the line, it's most uncertain. That dividing line is the decision boundary. For logistic regression, it's always straight, simple, but often surprisingly effective. To fit it, we use the laws from episode 13, cross entropy, push the weights so that correct answers get high probability and wrong ones get low. Unlike plain linear regression, there's no one-shot formula here, so we train it with gradient descent. Same machinery as a neural network, just one tiny layer. Both models can overfit when features are many, so we regularize, exactly as in episode 7. Add an L2 penalty and you get ridge regression, which shrinks the weights smoothly. Add an L1 penalty and you get lasso, which drives unimportant weights to 0 and effectively selects features for you. Simple models kept disciplined. So there's your starting pair. Linear regression fits a line to predict numbers. Logistic regression bends that line through a sigmoid to predict probabilities. Both are fast, transparent, and are not coincidentally single neurons in disguise. Always run them first. If a billion parameter model can't beat a line, you've learned something important. Next time, a model that doesn't learn a line at all, it just remembers k nearest neighbors. See you there.